Hi, I'm honored to present to you Splatent, Splatting Diffusion Latents for novel view synthesis, accepted at CVPR 2026. Popular novel view synthesis representations like NERF and 3D Gaussian splatting traditionally work in RGB space. Recent methods explore 3D-GS in the latent space of diffusion VAEs instead. A prominent example is MVSplat360. It predicts 3D Gaussians from a few input views, renders features directly in the VAE latent space, and then uses a video diffusion model to clean up the rendered features before decoding. This tight coupling with a diffusion pipeline is attractive, but as we'll see, it hides a subtle problem. As shown in qualitatively, the problem is hallucinations. The video diffusion model often invents content that does not match the ground truth scene. For example, look at the highlighted regions in these rendered outputs. So we asked, why does the diffusion model need to hallucinate in the first place? The answer lives in the frequency domain. We analyze latents for multiple popular VAEs, Stable Diffusion Turbo, SDXL Turbo, and Flux. As you can see, they contain far more high-frequency content than in the RGB domain. Critically, those high frequencies are view inconsistent. When 3D Gaussian splatting averages conflicting signals during optimization, the high frequencies cancel out. What remains is only low-frequency structure, which produces blurry decoded outputs. This is also visually prominent, as shown here in this rendered feature from 3D-GS optimization. Despite these drawbacks, latent rendering is still worth pursuing. It brings real benefits: faster optimization, seamless integration with latent diffusion pipelines, and direct gradient flow for end-to-end feed-forward training. Still, viewing consistent high frequencies remains the core challenge. We need a principled way to put the missing details back, using multi-view attention. So we do not need to fix the 3D representation itself. Instead, we enhance each rendered view in 2D using the nearest neighbor views as a source of truth. Here is our pipeline. First, we encode each input view with a frozen VAE and optimize the latent 3D Gaussian splatting representation. This 3D representation captures the low-frequency, view-consistent geometry of the scene, but collapses any view-dependent details. So when we render a novel camera, the resulting latent has missing high-frequency details, because those frequencies cancel out during optimization. This is the degraded latents we need to enhance. Next, we tie the render latent together with the three closest reference view latents into a spatial grid, and pass it to a fine-tuned stable diffusion single-step model. During denoising, multi-view self-attention propagates high-frequency details from the references into the degraded rendered view. We then take the refined top-left tile from the grid and decode it back to image space using the same VAE. Importantly, the VAE never changes, it is kept frozen. This preserves the original reconstruction quality and keeps our approach compatible with any pre-trained latent diffusion model. The grid arrangement and the reference view selection strategy are bladed in the paper. We evaluate our method on DL3DV, LLFF, and MIPNERV360 datasets. Splatent sets a new state-of-the-art for latent radiance field reconstruction. We outperform competition across PSNR, SSIM, LPIPS, and FID in both dense view and sparse view settings. Noticeably, Splatent is trained only on DL3DV, but generalizes strongly to the other benchmarks. Qualitatively, Feature 3D-GS loses most fine details. LRF improves the baseline, but still blurs textures. Splatent produces sharper, more faithful reconstructions, with clear detail recovery on text, tilework, and vegetation. Our refinement module also plugs directly into feed-forward models. With Splatent attached to MVSplat360, hallucinated details are replaced with faithful reconstructions from the reference views, and every metric improves. The two methods are complementary. MVSplat360 brings the generative prior, Splatent enforces fidelity. To summarize, we analyzed why latent space radiance fields lose detail, and showed that injecting high-frequency content from reference views through self-attention in a single-step diffusion model elegantly solves this problem. Splatent enables efficient, high-quality 2D reconstruction in latent space. Thank you for listening.